All right, so let's start our last and final unit. It's still going to be with integration, but we're going to look at different theorems and properties, and we're going to kind of bring back that idea of area under a curve kind of later in this unit. We're first going to take a look at this section called the second fundamental theorem of calculus. Do we hopefully remember what the first fundamental theorem of calculus said? It's the top minus bottom idea, okay? When you have to work backwards, aka find an antiderivative, and then do top bound minus bottom bound. Okay, that's the first fundamental theorem. We're going to take a look at the second. It's going to be kind of similar, but I think we're going to start to see a shortcut or a pattern after a while, which hopefully makes it kind of easy for us. So this first page is just going to be kind of an investigation. Do we notice anything kind of interesting happening? And then we'll get into some more examples after we talk about it. So for this definition at the top, given the functions f of t from below, use this equation. So capital F is defined to be the area under the f graph from 1 to x. Do you notice how this integral is a little bit different? Do you see how we have a variable as one of the bounds? Okay. Remember, a variable means you can choose to make that number whatever you want. So I'm not telling you specifically the area from 1 to 7, okay? I'm letting you decide, do you want to figure out the area from 1 to 5, 1 to 9, 1 to -2? Maybe we can switch those bounds. Okay, so we're going to use this statement to help us answer some questions about capital F, but then also the derivative of capital F. So let's try this first one. They give us the equation for f of t. Let's go ahead and just substitute that into the function for the integral. After all, they mean the same thing. So we can rewrite capital F as the integral from 1 to x of 4t minus t squared dt on the end. Are we okay with that substitution? Just a rewriting? All right, now we got to find two things. We got to find capital F of x in terms of x. Right now it's just in terms of t's. All right, so let's go ahead and use that first fundamental theorem of calculus where we can work backwards, find an antiderivative, and then we'll do top bound minus bottom bound. So let's try to work backwards. If you have a 4t, what did you have previously? 2t squared. And if you have a t squared, what did you have previously? A 1/3 t to the third. We'll draw in the bracket, and our bounds are from 1 to x. Okay. All right, so we plug in the top bound first. So that would be 2x squared minus 1/3 x cubed. And then we need to subtract what we get when we plug in the bottom bound. So we'll go ahead and plug in 1 for those t's. Looks like we'll have 2 minus 1/3, which we'll go ahead and write as 5/2. Or sorry, 5/3. So it looks like our final equation for capital F in terms of x's, because notice how we have x's now instead of t's. When we did that top minus bottom, bless you, it turned the t's to x's. So we have 2x squared minus 1/3 x cubed minus 5/3. I don't think that's too new to us. We're used to working backwards, antiderivative, top minus bottom. It works the same way. We just have a variable there instead of a number. The second thing we want to figure out is what's the derivative of capital F. So if you were to take the function we just found and do a derivative, what would you get? 4x minus x squared. Anything interesting with that derivative? Isn't it the same as f of t, just with x's instead of t's? That might be worth noting, okay? What if we tried the next one? Do you think you can anticipate what the derivative of capital F would be? Let's see if that works out. Okay, that's our little educated guess. All right, let's go ahead and though go through the actual work to find capital F of x. So we need to integrate from 1 to x, cosine of t dt. All right, so trig antiderivatives. If you have a cosine, what did you have before? What can you take the derivative of that would give you cosine? Sine. So this is sine of t. First fundamental theorem, top minus bottom, we'll have sine of x minus sine of 1. Do we know sine of 1? Probably not. That's not a nice radian value. So there's our capital F of x. If you were to take the derivative of that, the derivative of sine is cosine, but the derivative of sine of 1 would just be 0, because isn't sine of 1 a numbered value? It's a constant. Okay, so it looks like our guess was correct in the end. We're starting to see a pattern a little bit. Let's try another set. Okay, given the function f of t, use this integral to help you find capital F and capital F prime. Okay. Can we make an educated guess, perhaps, what capital F prime might be? All right, let's see if that's the case for this one. Okay, that's our educated guess. Now this one is just slightly different. Notice how the bound, upper bound this time is x squared. It's not just a single x. Maybe that might change something, who knows. So capital F is the integral from 1 to x squared of t cubed. If you work backwards from t cubed, what'd you have before? There we go, 1/4 t to the 4th. And then first fundamental theorem, top minus bottom. If we plug in x squared, we'll have x squared to the 4th. We'll have a power to a power. So we can multiply those to give us an x to the 8th. And then minus plugging in 1, which would just give us a 4th. So there's capital F of x. If we were to take the derivative of that, what would it be? Two x to the 7th. Does that match our educated guess of x to the 3rd? Not quite. Okay, so something's tricky here. The bound must matter. Notice how when it was just a single x, it kind of followed that pattern or just using the original function. But the moment we change the bound, it looks like that pattern doesn't really stay true. Okay, we'll talk about that in a little bit. But at least that's something that we notice. Let's go ahead and try the next one. So capital F, we got to integrate from 1 to x squared of 6 square root of t. Now, probably strategically, we should change the square root to a 1/2 power. That way we can easily kind of work backwards from that. Can we work backwards? If you have a 6t to the 1/2, what did you have before? Do you remember our reverse power rule? If we add 1 to the power, that would be 3/2, and then we have to divide 6 by 3/2, so kind of fraction work going on there. You'd eventually get 4. All right, first fundamental theorem, top minus bottom. If we plug in x squared, we'll have x squared to the 3/2 power. We can multiply those powers together. Looks like we'd just be left with 3. And then subtract what we get when we plug in 1, so that would be 4. If we were to take the derivative of capital F, looks like we get 12x squared. All right, that's not quite what the original f function was. So again, it looks like that bound matters. So what we're doing here is we're strategically analyzing what happens when we take the derivative of an integral. Notice how we found an antiderivative, but then we took a derivative, and sometimes we got back the original function that we started with, sometimes we didn't. Does it make sense in our heads that derivatives and antiderivatives are inverses of each other? They're kind of opposites. If you start with an original function and take a derivative, that's kind of one step. But if you were to take an antiderivative of a derivative, you would get the original function back, working backwards. That's kind of what's happening here. We're taking derivatives of integrals, and we're going to analyze kind of what happens and why the bound is pretty important. So we're going to write down the second fundamental theorem of calculus, and then we're going to see how those 4 examples from the front actually work out with this new theorem that we have. Sometimes the bound matters though, so we got to pay close attention to that. I'm going to write it down, and I want you to look at it and try to think about what it's telling us, or how you would describe it to someone. Yeah. Mm-hmm. All right, take a look at that block at the top. If capital F, they could name it anything, but in this case it's just capital F. If capital F is defined as the integral from some bottom bound to some upper bound, whether they're numbers or variables, doesn't matter, of some function, then if we were to take the derivative of capital F, which means taking the derivative of an integral, what would we get? Can you describe that craziness? What does it look like we did? Bless you. Maybe think about the first fundamental theorem of calculus, that whole top minus bottom idea. Can we see it? What did we do? Instead of finding an antiderivative and doing top minus bottom, like the first fundamental theorem tells us, if we're taking the derivative of an integral, there's no reason to find an antiderivative because we know we're going to be left with the original function we start with. It's like taking a derivative and then working backwards. You're back to where you started. but the bounds are important. Do we see that we took the upper bound and plugged it in to the function? Isn't that f of g of x? Then we're multiplying by the derivative of that upper bound, whatever it might be, a number or a variable. And then just like the first fundamental theorem, we're going to subtract, plugging in the bottom bound, so f of h of x, whatever this is, number or variable, whatever. That should be times the derivative of that bottom bound. Okay, so it's still top minus bottom, but if you're taking the derivative of an integral, there's no reason to work backwards. We're going to be back to where we started, but the bounds are important. We got to analyze what's happening kind of at the beginning and at the end. Okay, Colton, right idea, good. Okay, so instead of working backwards and then finding a derivative like we did on page 401, let's see if we can just find the derivative immediately now that we have this second fundamental theorem. So if you want to take the derivative of capital F, we could write that as capital F prime. And on the right-hand side, we're going to take a derivative of an integral. So there's no need to work backwards. We just need to take a look at those bounds. And it's always top minus bottom. So if we were to plug in the top bound into the function, we would get 4x minus x squared. But then we have to multiply by the derivative of that bound, which would be what? The derivative of x is just 1. Okay? To continue, we'd have to subtract what we get when we plug in the bottom bound. So that would be 4 minus 1 times the derivative of that bottom bound. What's the derivative of 1? 0. So notice how multiplying by 0, that's going to kind of cancel out what we get from that bottom bound. And we're just left with the 4x minus x squared. Doesn't that match what we had on the other page? Okay, isn't this a lot quicker than what we did on the previous page? Because if you take a look at the previous page, we rewrote what f of x was, we worked backwards, finding an antiderivative, we did top minus bottom, and we eventually simplified it. And after we simplified it, then we took the derivative. That's a lot of work, okay? But now that we have the second fundamental theorem of calculus, if we're trying to find the derivative of an integral, it's just simply top bound minus bottom bound, but we have to multiply by the derivatives of those bounds after each step. It's going to be a little quicker, kind of a shortcut for us to find the derivative of an integral. Let's try the next one. If we want to find the derivative of f, that means we'll have to find the derivative of an integral. No need to work backwards. We're just going to do top bound minus bottom bound, but times the derivative of the bounds after each set. So if we plug in the top bound, we'll get cosine of x times the derivative of that top bound, which would just be 1. Then we'd have to subtract, plugging in the bottom bound, so that would be cosine of 1, times the derivative of that bottom bound. The derivative of 1 is 0. So cosine of 1 times 0, that's going to go away, and cosine of x times 1 is just cosine of x. Doesn't that match what we got on the previous page? A lot less work though. Okay? The second fundamental theorem of calculus, if you're taking the derivative of an integral, there's no need to work backwards. It's still top minus bottom, but multiplying by the derivatives of those bounds. Let's try the next one, because this is when it got a little tricky. These were the ones that didn't really match the kind of pattern we noticed for the top two, where we thought the first one would just be x cubed. Notice how it was 2x to the 7th. So let's see how the second fundamental theorem of calculus can get the same answer probably a little quicker. Let's take the derivative of an integral. So we need to plug in the top bound into the function, but then multiply by the derivative of that top bound, which would be what? Would it be 2x? Next, we have to subtract what we get when we plug in the bottom bound. If we plug in 1, we'll get 1 times the derivative of that bottom bound, which would be 0. 1 times 0 going to go away, and we're left with x squared cubed, which would be x to the 6th, times a 2x. So that would leave us with a 2x to the 7th. That matches what we got before. So you got to pay attention to the bounds, because after all, you got to take the derivative of them eventually. Do you guys want to try the next one? Give it a shot. If you're taking the derivative of an integral, they kind of cancel each other out, but we still have to do top minus bottom. Just find those derivatives of the bounds. What's nice about this one is you already know what you should get in the end, because we already tested it. The next few we do, we don't know the answer, so we got to be a little bit more accurate, or aware, I guess. Let's see, taking the derivative of an integral, kind of cancel each other out because we're going to be back to what we start with, okay, essentially the function they give us. If we plug in the top bound, we'll have 6 square roots of x squared times the derivative of that top bound, which would be 2x, minus what we get when we plug in the bottom bound, so 6 times the square root of 1, which is 6. But multiplying by the derivative of that bottom bound of 1 would just be 0. So 6 times 0 goes away. The square root of x squared is just x. So 6 times x times 2 times x looks like we get 12x squared. Are we able to get that? Sound good? All right, let's try some more that we don't really know what the answer should be. So on the next page, we'll try the top 3. Do you guys want to give them a shot? See how you do? Try the next 3. All right, let's check out the first one. We might not get to the other two because the bell's going to ring in a little bit, but let's just see how we did on the first one. So if you're taking the derivative of an integral, they kind of cancel each other out. No need to work backwards. But we got to be careful with the bounds. So if we plug in the top bound, we get that, times the derivative of the top bound, which would be 2. Then we have to subtract what we get when we plug in the bottom bound. What's going to happen though? Can we anticipate it? It's going to be 0 because the derivative of the bottom bound is eventually going to be 0 times anything else is going to be 0. Okay, so we got minus 0. So in the end, if we want to move that 2 out front, we'll have 2 square roots of 2 minus 4x squared. 2x squared, you can square the 2 and square the x. There's the derivative of capital F. How'd you do? Pretty good? All right, let's see maybe if we can get the next one in. The derivative of an integral cancels out, but we still got to check the bounds. If we plug in the top bound, we'll get something times the derivative of the top bound, which is just going to be what? 0. But then we have to subtract what we get when we plug in the bottom bound. So this would be e to the cosine of x squared times the derivative of the bottom bound, which would be 2x. So if you want to rearrange it, maybe move the 2x out front, you can. 2xe to the cosine of x squared. There's your derivative. How'd you do? Yeah. Oh, negative, yep, sorry. Because we're subtracting. That's right. Is that better? Yes? All right, maybe we can get the last one in. Derivative of an integral goes away, but we still got to check the bounds. Plug in the top bound. We'll have cosine of x squared times the derivative of the top bound. Derivative of cosine. We got negative sine. Then we have to subtract what we get when we plug in the bottom bound times the derivative of the bottom bound. 0. So it looks like we're left with negative cosine of x squared sine of x. Or however you want to rearrange it. How'd you do? Pretty good? All right, derivative of an integral, they're inverses, they cancel, but we still got to check the bounds. We'll try more tomorrow.